All right, our next talk is from Bob Buchheim, Time Series Spectroscopy of Flare Star AD Leo in 2021.
Excellent. One of me is more than enough. Since these stellar flares occur randomly and infrequently, detecting them means devoting an enormous amount of observing time. And that means that this whole flare project falls into one of the sweet spots for the backyard observer. We can squander our observing time however we want, whereas the professional observers are dealing with time allocation committees, and it's really, really difficult for them to say, I'd like to stare at this one star all night, every night for 2 months. We can collaborate, as you've seen, across continents to keep the star under more continuous observation than the professionals ever could. And so it fits into our ballpark. Last year, I gave an overview of what we had done on AD Leo in the 2021 observing session. And the question there was, can we see flares at all? And the answer was unambiguously yes. Here's a plot like Woody showed of equivalent width on the vertical axis versus time on the horizontal axis, showing the equivalent width of Balmer line H alpha, beta, gamma, delta. And you can see that characteristic flare in the signal. The reality of our detections, as I reported in 2021, was validated by the fact that there were several times where Woody and I, separated by about 20 miles and using different equipment, were watching the same star at the same time and saw the same flare. So it's not a local artifact. It was also validated by the fact that the parameters that we were seeing and the effects we were seeing, as Woody described, are very similar to the parameters and effects that you find in the professional literature on stellar flares. We also identified some things that we wanted to do with our data now that we believed we were really seeing something, and that had not been done then. So what I'd like to talk about today is one of those to-dos, which was, let's do a quantitative statistical analysis of the flares that we detected during the 2021 campaign on AD Leo. So I'm going to describe how we translate equivalent width into flare energy, how you take the flare energy of each individual flare and create what's called a flare frequency distribution, which will answer part of Mike's question about how many flares per hour at different energies. I'll show some of the other properties that we observed in this flare collection, and then some lessons that we've learned and some enhancements that still need to be made in what we've done. You've seen this spectrum, M-class dwarf star, and AD Leo is a perfectly normal M-class dwarf, except it has emission even in quiescence. These emission lines never go away. But if I zoom in just as an example on H gamma, here's what the H gamma line looks like in quiescence. And this is what your spectrum will show. You take a series of 3, 4, 5 minute exposures all night, and you'll see this over and over and over again until at one point you discover that it's rising a little. And that increase in emission line strength grows and finally peaks out, often within 3 or 4 images, so 10, 15 minutes. And then it starts to fall back again, and eventually, in the fullness of time, returns to the quiescent level. So we characterize that effect, by that event, by the equivalent width of the emission line as a function of time. Equivalent width is in the textbook model. You see a plot of flux versus wavelength. There's a continuum level shown in red, and the emission line peaks up above there, and the textbook definition for calculating equivalent width to tell you the strength of the line. And we call that EWQ because it represents the quiescent or quiet status of the star. Then something happens. The emission strengthens. You can still calculate an equivalent width, but now we call it EW at time t, because that's what it was when this particular image was taken. And that's the equation then that enables you to make those plots of equivalent width versus time. The shaded area there, the growth above the quiescent level, turns out to be representing the power in the flare, the increase in power emitted by the star because the flare is happening. And fortunately, there is a pretty simple relationship between the change in equivalent width, EW at time t, minus the quiet level, and the power instantaneously emitted in the flare. And this is the equation. And the parameter F sub c, which is the conversion constant between equivalent width and power, is the flux level of the continuum underlying that emission line in ergs per second that measured at the star. We did not have simultaneous photometry during 2021. And what that means is we could not flux calibrate the individual spectra as the event transpired. So weakness number one, I'll acknowledge right now, this has hidden in it the assumption that as the emission line was pooching up, the continuum level was staying constant. David will show now that we're doing flux calibrated spectra, that's not actually true. So the energy calculation, power and energy calculations I'm making here are in some sense a lower limit to what the flare is emitting. You take power versus time, integrated over the duration of the flare, that tells you the total energy in ergs that the star emitted during the flare. So here's a typical example. On this particular night, plotting equivalent width versus time for most of a night. The horizontal red, the equivalent width vertical, time horizontal, the red horizontal line is the quiescent level of equivalent width. And you can see there's a little bouncing around of the individual data points. Some of that is normal measurement noise. Some of it is what Eric would call sizzling. We call burbling on the star. You translate that using the equations shown on the prior slide. I'm sorry. You identify the flare, right? And this particular night, looks like there were two events. Flare number one, big, easily recognizable, fast response, gradual decay. And flare number two, more of a small hump with a somewhat different shape. Translate that using the equations from the prior slide into a graph of power, ergs per second emitted by the star on the vertical axis versus time, obviously very similar shape. But now we know the power being emitted by the flare out there at the star, and integrate that over time, over the duration of the flare, to determine how many ergs the flare was emitting. Now, and as I mentioned, this represents the power in this case, the H gamma emission line, not the total power emitted, but just in this one line. But now you do that for all of the lines of interest where the emission peaked up, sum over them, hence the need for that special software database that Woody described, so you don't end up doing that by hand. Detecting the flares is a tricky business. I've mentioned they come in different shapes, they come in different sizes, some big and tall and easily measurable, some that are so kind of down there in the sizzling or burbling that you wonder if what you're seeing is real or not, which it may not be, and of various durations. You can see these two, flare number two is much shorter total duration than flare number one. In the professional literature, you will find a variety of groups that are developing pretty sophisticated flare finding algorithms. And if you're into that kind of math, you can probably imagine how they might go about doing that. One of the things about most of those algorithms is ultimately they have to be tailored to the peculiarities of your instrument, what you're measuring, what your observing cadence was. And so frequently they have to be combined with some sort of eyeball validation to get an assessment of false alarm rate and detection probability. I'm not a math guy, and I'm pretty simple-minded. So what I like to do is go back to the papers from the 1960s, where they did a visual examination and said, looks like a flare to me, looks like it started here and ended here, and then do the calculations. So that's the approach that I took in the results that I'm about to show here. Flare detection was a purely subjective eyeball assessment of did it flare and when did it start and when did it end. That obviously needs to be put on a little more quantitative statistics basis. Probably be back next year to talk about that. One of the statistical descriptors, now that we have a catalog, an atlas of a whole bunch of flares from this star in the same observing season. Oh, I mentioned that. The visual flare detection algorithm I used was, first of all, check the statistical significance of the fluctuations in equivalent width from the EW stats program, demand that there be a 3 sigma change somewhere in the course of the night. A plausible shape of equivalent width versus time spanning at least 3 data points above the quiescent level, visible in at least 2 emission lines, and then make a visual estimate of start and end times. Get the energy in each of the flares in the database. And one of the standard statistical metrics is what they call the flare frequency distribution. And it's the cumulative distribution function of number of flares or flares per hour versus total energy. It gets at question Mike asked about, do they all have about the same size and how often do they happen? The standard observation is you're a lot more likely to see a small flare than a big one. And the standard model is a power law shown in the equation up there, with it that the flare rate falls off as some exponential of the flare energy. So let's plot the cumulative energy distribution, number of flares per hour on the horizontal axis and flare energy on the vertical axis. And I emphasize this is the cumulative distribution. So each data point is going to be the flare rate for flares of that energy or larger. That plot would be a straight line on a log-log graph, but we're going to expect to see 2 observational bias effects. One is that at the flares with really low energy, at some point our signal level doesn't permit us to detect them above the noise, whether it's measurement noise or astrophysical noise. So we kind of expect the curve to turn down at that end of the curve. At the high energy end, even with a 2-month-long project, we may not have observed long enough to see the really, really big flares. So we expect that there may be some kind of raggedness of the data at the high flare end. That's what you expect to see. So catalog all of your flares, put them all in order of total energy, sum up the energies in all of the Balmer lines to put a single number on each flare. And here's what you get. Energy in ergs, log, flare rate in flares per hour on the horizontal axis, and each dot represents 1 observed flare. Not a bad match to the linear fit expected from a power law distribution. You can see how on the right it turns over. as kind of expected from observational bias. And at the high energy end, the data pretty well sits on that straight line all the way to the largest flare we saw. Turns out that is also something you see in a lot of the flare frequency diagrams in the professional literature. There's always a point where the flare is too small to detect, so the curve bends over on the right, but usually the data points stay a reasonable match to the power law expectation at the high flare rate end. Now, this is the sum of the bomber lines. If you compare this with a published, professionally done flare frequency distribution on the same star, albeit photometry measurements in U band, it's even got the same slope. And this is an example of the sort of thing we say, we're seeing the same kind of parameters that the professionals are seeing. Now, my data points here are the sum of the alpha, beta, gamma, delta bomber lines. Oh, let's see, I've said we've seen that. If you break that up into the individual lines shown in color, you find that H alpha dominates the energy budget, followed by beta, followed by gamma, followed by delta. It's also worth noting on the prior slide, the units on the horizontal axis, that turnover where the flare is no longer large enough to be reliably detected is at log flare rate of minus 0.9. That translates into average 1 flare per 8 hours. So all night, you got about a 50-50 shot of seeing something. And if you want to detect a flare that's 10 times as large, oops, you've got to observe for 10 times as long. Hence, an opportunity to spend a lot of observing time. I made the comment on the earlier chart about the different shapes of the flare power distribution or flare equivalent width versus time between what we call the FRED, fast response exponential decay, versus the gradual flares. Where do those shapes fit into this flare frequency diagram? So I've highlighted in red the flares that showed the gradual shape, and in black is the FREDs. And you sort of get this hint that the gradual ones tend to be lower energy. However, I got to admit, I don't know what that might mean. And I don't even have a good, strong feeling about whether it's real or some kind of an observational bias that you pick out the big ones because they look like a FRED. So the only safe conclusion from this chart is that more data is needed. I mentioned the flare identification algorithm in my imagination that I'm using looks for that rise and fall of equivalent width in at least 2 of the bomber lines at the same time. Here's a plot over the entire data set of the equivalent width in the H gamma line on the horizontal axis and the equivalent width of the other bomber lines, alpha, beta, delta, on the vertical axis. And you can see, here's in blue is H delta and in orange is H beta, and the open circles are H alpha. They're all kind of straight lines. They're all correlated. When one goes up, they all go up. So that's good. However, this hides an interesting phenomenon. If you zoom in on just the single largest flare observed in this campaign, and we're going to plot equivalent width versus time for alpha, beta, gamma, delta bomber lines. You see the flare visibility effect, which is pretty common in what we're seeing. H gamma is the one that has the greatest visibility. It's down at the blue end where the star is inherently faint, so it captures your eyeball a lot more cleanly. But remember, there's more energy coming out in H alpha despite the smaller equivalent width change. Do that full width half max calculation of the duration of each of these events, and based on the change from the quiescent level to the peak of the line. And I'll go through the emission lines kind of in inverse order, starting with H delta. That's the full width half max of H delta. Next redder line is H gamma, then H beta, then H alpha. There's a pretty clear trend that the full width half max is getting broader as you look at the redder emission line. This is something that's been reported in the literature. I think it has something to do with the way the stellar atmosphere is relaxing from that heat pulse when the magnetic lines did their thing to start this flare. It's called the Balmer time decrement. It's been reported in the literature, and we're seeing the same effect in our backyard telescopes. It's also worth noting there was a question about the durations. This particular event had a duration start to end of more than 3/4 of an hour. Thank you. Again, as you can see over on the right side, we never really got down to quiescence as the star was setting. I went through the whole atlas of AD Leo flares in 2021, and here's the histogram of the flare duration from the start when it first rises above quiescence to the end when it goes back down into quiescence. On average, they last about an hour, but the range goes from little pipsqueaks, only about 15 minutes long, and the limit there is obviously an observational effect. I'm taking 5-minute exposures. I demand at least 3 data points. You can't count anything less than 15 minutes long, and there's a few that last 3 or 4 hours, and that too is an observational effect, because in order to believe your detection, you need some time period at quiescence, then the flare event, and some more time at quiescence. In a 6-hour observing run, you're not going to recognize anything that lasts much longer than 3 or 4 hours. I think that on EV LAC, there was an event that David in England saw the rise, peak, and fall, and it was way not down to quiescent level. And then several hours later, Woody in Arizona saw the decline continuing. That might have been, an 8 or 9 hour flare, but unfortunately, we don't know what happened in between times. How come I'm not moving here? Okay, this whole thing came out of the spectroscopy discussion group that Woody had started shortly after the spectroscopy workshop in Las Cruces several years ago. Here are some, but not all, of the people who have been involved. I thank each and every one of you. Woody for setting this up, for everybody for getting kind of excited about this project when it was still unsure whether we could see anything meaningful. Everybody brought energy, enthusiasm, dedication, cameras, spectrographs, and data to the party, ideas and questions about how to analyze it. Special thanks to James Jackman, Chris Corbali, and Steve Shore, who have been our spectroscopy mentors through this journey in the darkness. Well, I did it again. Oops. Okay, so conclusions. We're not only detecting flares, but now we've shown that we can measure their properties. We've been able to replicate phenomena that have been previously published in the professional literature. We've got a big flare atlas waiting for additional analyses. I am sure that there is more yet to be teased out of them. We have all paid a lot of attention to a corner of the professional literature that we probably never would have read had it not been for the enthusiasm here. Two big weaknesses: the lack of simultaneous photometry, so we could not flex calibrate the spectra, and the purely visual approach to detecting the flares. And as you've seen from Woody's talk, we're figuring out how to put both of those on a more solid mathematical basis. Observing these with simultaneous photometry, you're going to see from David some of the things you can see. Another limitation is, as you saw on the photometry curves earlier, rapid photometry time series is feasible. Stars are reasonably bright for a good sized telescope, whereas we need longer exposures in the spectra. But it would sure be nice to have finer time resolution in the spectra. So Woody started running some experiments with not 5 minute, but 4, 3, 2, 1 minute exposures to see if we can tease out time evolution without burying it in the lower signal to noise ratio. We've got a gang of high resolution spectra that need to be evaluated for things like spectral profile changes, radial velocity effects, and the LISA and UVEX spectra are probably able to tease out increases in some helium lines and maybe others during these high energy events that we also have not examined yet. So Rachel has told me that I'm out of time. Otherwise, I'd be happy to entertain a question.
We have time for a couple of questions, and we have a couple of questions.
Thank you. This is really neat work. Except most of us only have one telescope and one night a night to do the work. The question I have is, you have calculated the energy ergs in the increased size of the emission peaks.
Mhm.
Okay. Is it feasible to ask the question? Well, it's easy to ask the question. Is it feasible to answer the question? Is all of the increase in brightness of the star as shown in photometry, how much of that is going into the peaks rather than a more subtle, much lower increase in the overall phase?
Perfect introduction to David's talk.
Well, you paid me to do it.
Yeah, it is possible, and David will show us how.
I have two questions, Bob. I love this project. The first is for the flare that was observed in UK and then picked up again in Arizona. I know this is a little unfair, but do you have any sense that the shape of that flare mimicked what you were seeing in these other flares, the very rapid rise and the slow decay?
Yeah, it looked like a classical Fred flare, and we got it up and then a big gap and then it was still coming down.
And that was roughly a 9-hour duration.
It must have been, if it was a single event.
Yeah, and so the second question I have,
and I hasten to add, we have also seen flares, lasting 2 or 3 hours, where you see the rapid rise, the decay phase, and then another rise and decay.
Yeah.
And where in this analysis, I treated those as 2 events, calculated the energy under the bump and then the energy in the more classical event.
yeah, I'll reiterate and that is you have this huge accumulation of flare events. What is your publication status at this point, or schedule, or whatever?
I think you just saw it. But yeah, if you'd like entree into the atlas, send me a note.
I'll do that. Thank you. This is a great project.
So let me ask Jessica Draper to unmute and ask her question. Go ahead, Jessica.
Hi, I had a question about one of the earlier slides where we were looking at the time series of the two flares. There was flare number 1, and then later on there was flare number 2. And I was just wondering, it almost looked like there was a third flare in there, another small one, because some of the data was missing. I'm not sure if the star maybe went below the horizon or something. So right above the label where it says flare 1, is it possible that it actually came down and went back to the continuum, and then just after that came back up for another small flare? So there's actually one in between the large one and the small one.
Yeah. Hi, Jessica. I'm sorry you couldn't be here in person, but glad to know you're online. Yes, in fact, you'll see that there's a gap in the data. For those of you in the room, that's right here. That's meridian flip and calibration lamp and things like that. And what you're suggesting is a reasonable interpretation. I looked at that and said, I'm going to treat it as a single event because I don't have evidence of where the first peak faded back to quiescence, but it could very, very well have been 2 events.
Very interesting. Thank you.
So a comment, when you were looking at Fred's and the graduals, okay, and that distribution that you have, it appears off of sparse data that the graduals are much less common than the other ones. And given the statistical distribution of the flares that you've met, you would expect that since the high energy flares are rare, that the higher energy graduals are far more rare, and you should see them drop off the end of the graph.
Yeah, and in fact, now this is me, and I'm not much of a statistician, but I have the same kind of observation you do, and the following concern. If you remember a graph that Woody showed where we stacked the equivalent width night after night. Now, albeit that was a different star and a different year, but if you go down to the bottoms of those columns, the bottoms did not hit a single level. One night, the smallest equivalent width you see is higher than the smallest equivalent width you see the next night. Now, from a practical standpoint, where you're doing visual detection of the flares, you say, hey, I've got a nightly level, I'm going to call it quiescent, and that's it. But what if the quiescent level went up and down for 20 hours? Is that a 20-hour flare? Is it some other astrophysical event? I have no idea, but there's an observational bias hidden in there.
Okay. And then the other thing is, would observation through narrowband hydrogen alpha photometry help you do a better job of quantifying your energy levels, or be able to run it?
I don't know. Wayne has argued in favor of that.
Yeah, I think that, if you want to see the energy in that band, admittedly, instead of looking, the width of an H alpha filter,
40 or 50 nano angstroms.
Yeah. Versus looking at the continuum in a red filter, I think it's just got to give you better fidelity.
Yeah. And there's a whole lot of history that says if you're photometrically detecting these events, get into B band or U band. They're high energy, presumably high temperature, and there's a lot of data that says that's the case. But yeah, looking at narrow band focused on an emission line, it'd certainly be an interesting experiment.
And some of these dual band filters that do both hydrogen beta and hydrogen alpha, and then cut everything else. Well, they'll let oxygen sneak in, but would be perhaps an even better tool.
Wayne, did you want to weigh in on that? Wayne's been one of the proponents of doing just that. Okay, apparently I'm out of time.
Hi, it's Wayne Green. hydrogen alpha is kind of useless with darker red stars like DM5s and cooler because of line blanketing that takes place up at that end of the photosphere. It's difficult to achieve things. Hydrogen alpha, beta, gamma, delta, and so forth in this event are all tied together because we have a massive multi-messenger explosion going on, everything from hard X-rays down to radio. So if you go back and you look at the hydrogen beta lines, I guess I should hold the mic up a little bit better. If you go back and look at the hydrogen beta lines, you find they're pretty much in lockstep, hydrogen beta, excuse me, beta, delta, gamma, all the way down. You get down near the Baumol decrement, just past the end of the B band filter. So the U band filter, now you're in the Lyman alpha regime, is pretty much useless for us at the low atmospheres because we just don't get enough transmission for it. Earlier, I had suggested using a hydrogen beta filter because they were havable at the time, and some people may have had them. Turns out that the Johnson B band filter includes enough of the combinations of beta, gamma, delta, and so forth to make a really good indicator, photometric indicator of these flares for flare frequency observations. And that work was reported in the literature, and I can't remember the author right off my top of my head, it was sometime in the 1990s. So yeah, what you can do at home with your narrowband filters is one thing. What you can do if you have a Johnson B filter, that's the filter of choice for doing photometric monitoring of these events.
Okay, thank you.